Welcome back. In our last lecture, we had studied about the different kind of vibratory systems, different kind of vibratory body, and different kind of vibrations, classification of vibrations, and natural frequency. Today, we are going to study about the equation of motion to find the natural frequency. Right. There are three kind of methods to solve the equation of motion to find the natural frequency. Whereas first is the equilibrium method, second is the energy method, and third one is the relay method. Now, what is the equilibrium method? We had to study about the terminology of the spring and the properties of the spring to find or to solve the equation of motion to find the natural frequency. First is the X, stiffness. Stiffness of the constraint. Right. Stiffness is the property of spring, which is the force required force. Means stiffness is the force required to produce a unit displacement of the direction of vibration. Right. Means stiffness is the force which is required to produce a unit displacement in the spring in the direction of vibration, and it is usually expressed in Newton per meter. In our first figure, it is the spring which is hang on a high, okay, and second part or second end, other end is free. Okay, means only one end is fixed with the ceiling or with the height, right? And other end is free. So this is the unconstrained position. What? Because the one in one direction we can expand the spring unlimitedly, independently, right? If the both ends are fixed, then this expandation, this limitation of expand, right? Means whenever you provide the external force to the spring, if the both ends are fixed, then the expandation limit of the spring is fixed. So the position is called constraint position. But here one end is free, then the one end of expansion of the of that direction is indefinitely. So it's called as the unconstrained position. In our second figure, I fix the mass at the other end, or you can say the free end of the spring. Then what happens? The some static deflection due to the mass of the weight, or you can say the gravitational force. Due to the gravitational force, the static deflection takes place by the spring and is equal to the restored energy force or restored force. Okay, means restoring force. The gravitational force which is produced due to the weight is stored in the spring as a elastic energy or strain energy. Now, if I in the last figure, if I give the external force to the spring or external force to the mass, then the static deflection plus the displacement given to the body with the help of external force is also included. Means the total external force is converted into the static energy, right? Means total force which is given to this spring is converted into the elastic energy or strain energy, and which is converted into the kinetic energy and try to regain its original position, and this kind of process produce the vibration in the system. Okay, so here the total force which is external force, means total external force which is given to the system is m d square x by dt square plus the gravitational force which is generated due to the mass of the system or mass which is fixed at the free end of the spring is w. Okay, means total force which is generated is m d square x by dt square plus w, and total displacement which is take place with the due by the spring is s into delta plus x, when delta is the static displacement and x is displacement given to the body by the external force, and s is the stiffness of the spring. Now, next. Now, w is the weight is given as the mg, and which is force of the spring or balance force of the spring is taken as S into delta. Now, as discussed earlier, restoring force is equal to W minus S delta plus S. Okay, restoring force is what? Restoring force is the accelerating force, or you can say the external force which is given to the system. Okay, restoring force is equal to the accelerating force or external force which is given to the system and is equal to total force minus W, right, is W minus S delta minus Sx. And accelerating force is mass into acceleration, and mass is m, and acceleration is d square x by dt square, which is given to the accelerating body, or you can say the spring or vibratory system. Now, the accelerating force and restoring force are same and equal value, so we can equate both the equation. Equating the equation of restoring force and accelerating force, m d square x by dt square is equal to minus sx, or we can get the m d square x by dt square plus sx is equal to 0. Now we are going to divide whole equation with the help of mass. We can get d square x by dt square plus s divided by m into x is equal to 0. Now we know that the fundamental equation of the simple harmonic motion for the wave or any kind of the rays is d square x by dt square plus omega square into x is equal to 0. Now, both equation, first we get the equation by comparing the restoring force and accelerating force, and second one is the simple harmonic motion equation for the waves. We can get omega is equal to under root s divided by m, which is the wavelength. Omega is wavelength under root s upon m, and the equation for the natural frequency Fn is equal to 1 upon Tp. Okay, where the Tp is the time period, Tp is time period and is equal to 1 upon 2 pi under root s upon m. So we can take Fn is equal to 1 upon 2 pi into omega, or you can take Fn is equal to omega upon 2 pi, right? So the time period is also taken as Tp divide is equal to 2 pi upon omega, or you can say that time period is equal to 2 pi under root m upon s. Now the total value of delta, total value of delta, and taken the value of g is 9.81 meter per second square is the acceleration. Gravitational acceleration is 9.81. We get the natural frequency Fn is equal to 0.4985 divided by under root delta. Right? This is the equilibrium method to solve the equation of motion to find the natural frequency, and we can get the final answer Fn is equal to 1 upon 2 pi under 9.81 divided by delta. Now we are going to next method. We are going to direct this second method is energy method. Okay, and what is the energy method? So in this method, we are going to study about kinetic energy and potential energy, which is restored or which is stored in the vibratory system or vibratory body. We know that the kinetic energy is due to the motion of the body, and the potential energy is with respect to certain datum position, which is equal to the amount of work required to move the body from the datum position. Right? Means kinetic energy which is generated in the system due to its motion. Okay, any kind of part which is in the motion is generated the kinetic energy, and the potential energy is stored energy, or it is an internal energy which is due to the datum position which is acquired by the body or acquired by the system. Now, in the case of vibration, the datum position is the mean or equilibrium position at the which the potential energy of the body or the system is zero. Okay. Now, suppose the system is into vibrating. Okay. If vibration is generated in the system, then what happens? Then the position which is acquired by the system or acquired by the body is continuously displaced, and which is, if we think the body or the system is equilibrium system, then the potential energy and kinetic energy means derivation of potential energy or maximum potential energy derivation is equal to zero. In the free vibrations, no energy is transferred to the system or from the system. Therefore, the summation of kinetic energy and potential energy must be constant quantity, which is same at all the time. Okay. In the free vibration, the energy not transferred or no energy is transferred from the system or to the system. Why? Because in the free vibration system, the axial force is released after taking initial. Means no axial forces is taken place during the whole process. So the no energy is transferred to the system and from the system. So the total energy which is in the system is going to constant. Yes, only the energy which is potential energy and kinetic energy is converted with each other. So the amount of kinetic energy will change, the amount of potential energy will change, but the summation of kinetic energy and potential energy is going to be constant. So any kind of derivation of constant value will be zero. So derivation of kinetic energy plus potential energy is zero. Next, we know that the kinetic energy, the equation of the kinetic energy is 1 by 2 into m into dx by dt whole square, and the equation of potential energy is 0 plus O plus 3x square by 2 into x is equal to 1 by 2 sx square, right? So the both equations we have to derivate the kinetic energy and we have to derivate the equation of potential energy. We get the equation m into d square x by dt square plus sx is equal to 0, or we can write as d square x by dt square plus s by m into x is equal to 0. The time period and the natural frequency may be obtained as discussed in the previous method as equilibrium method. The natural frequency, the equation of natural frequency is taken as S upon m. We have to equate the S upon m is equal to omega square. So omega is equal to under root S upon m. And we can take that the S omega is equal to 2 pi fm. Right. So with this equation, we can find the natural frequency as we have discussed in earlier method, energy equilibrium method. Now, the second method is the Rayleigh method. Okay. In the Rayleigh method, the maximum kinetic energy at the mean position is equal to the maximum potential energy at the extreme position, assuming the motion executed by the vibration to be simple harmonic. Means the maximum kinetic energy at the mean position, its other position, and the maximum potential energy at the extreme position is also other positions. Means we have to take the maximum kinetic energy at the mean position and we have to take the maximum potential energy at the extreme position. We can find the both equation as kinetic energy is 1 by 2 m omega square x square and maximum potential energy at the extreme position is 1 by 2 s x square. Equating both equation, we can get omega is equal to under root s upon m, and we can find the natural frequency fm is equal to 1 upon tp, or we can write omega upon 2 pi. So we can find the natural frequency is equal to 1 upon 2 pi under root s upon m. So next, natural frequency of free transverse vibration. Okay, we we have discussed for three all kind of methods. First is the equilibrium method, energy method, and third one is Rayleigh method. All for the longitudinal method, longitudinal vibration. Now we are going to study about the natural frequency for free transverse vibrations. In this transverse vibration, we had studied in the last lecture that when the body is oscillate, when the body is oscillate, then the vibration which is produced in the system is called as the transverse vibration. Now here, after applying the external forces to the body, the W or shaft is going to oscillate with respect to time. Then position after time t, after t seconds, the W weight is here. Then the static deflection delta and accelerating deflection x is taken place. So the mass, the force which is generated, means external force or accelerating force generated m d square x by dt square is equal to s into delta plus x. Okay, means sx is the restoring force, where accelerating force is m d square x by dt square, which is equivalent m d square x by dt square is equal to minus sx. So we can get that d square x by dt square plus s by m into x equal to 0. Okay, same as before, same equation which is generated or which is solved by us in longitudinal vibration, we can get the free transverse vibrations. We can get the natural frequency Fn is equal to 1 upon Tt is equal to 1 upon 2 pi under root S upon M. Now, there are many kind of deflection, many kind of other beams like cantilever beam, simply supported beam, cantilever beam with uniform distribution load. All kind of beams having a different kind of deflection. During the transverse vibration, we have to solve or we have to remember all different kind of deflection which is produced in different kind of conditions of the shaft. Next, damp vibration. What is the damp vibration? We have earlier studied in last lecture that what is the damp vibration, what is the damp free vibration. Okay, when the vibration produced in the system or when the external force is released or when the external force is continuously applied to the system, which is having the resistance or which is having the resisting force of the external force in the system is called as the damp vibration. Okay, right. Suppose as an example, if you are applying the external force to the body or applying the external force to the system, then the resisting force or a component of the system or component of the body or one kind of part of the machine which is oppose that external force or absorb some kind of energy to decrease or to decrease the vibration. Okay, so it is called as the damper. And if the damper is available to the system during the external force is generated or during the free vibration, the vibration produced is called as the damp vibration, right? So simple definition is it is the resistance to the motion of vibrating body. The damper is the resistance to the motion of the vibrating body, and the vibration associated with this resistance are known as damp vibrations. And the coefficient of damping is denoted by C. Next, critical damping coefficient. The critical damping coefficient is the amount of damping required for the system to be critically damped. Okay, when the system is equilibrium position and we are applying the axial force, then vibration is produced. But here, if you are applying the axial force to the system, but the whole energy or whole force energy which is produced due to the axial force is absorbed by the damper, then the vibration produced is zero. Okay, so this kind of condition is called as the critical damping. Okay, so critical damping coefficient Cc is equal to 2m under root s upon m, means the total 2m into omega n. Now, the damping factor, or you can say it's a damping ratio. It is the ratio of the actual damping coefficient to the critical damping coefficient is known as damping factor, and it is denoted as C upon Cc is equal to C upon 2m into omega. There are three conditions for the free vibration or free damped vibration is damping factor, or you can say the damping ratio zeta is greater than 1, then the system is called as the overdamp. If the zeta or damping ratio is equal to 1, then the system is called as the critically damped. And zeta or the damping factor is less than 1, then the system is called as the underdamped. Next, logarithmic decrement. Logarithmic decrement is the natural logarithmic of the amplitude reduction factor. In the amplitude reduction factor is the ratio of two successive amplitudes on the same side of the mean position. And the equation of the delta or equation of the logarithmic decrement delta equal to log e xn upon xn plus 1 equal to ATP equal to 2 pi into c divided by under root c square minus c square, where a is equal to c upon twice n. Right? So today, next topic is critical speed. The speed at which the shaft runs so that the additional deflection of the shaft from the axis of the rotation becomes infinite is known as the critical or reeling speed. Reeling speed. Sorry. The speed at which the resonance will occur is known as the critical speed, and resonance is the condition at which the induced frequency is equal to the applied frequency. Okay, are you understood? So let's take an example. If I apply the actual force to the vibratory body, okay. Now I have released the actual force from the vibratory body. Now the vibration which is produced after the releasing the actual force of the vibratory body is called as the free vibration, right? Now, at that time, when the free vibration is produced during the system, the frequency which is measured is called as the natural frequency. Now, when I am going to apply the actual force during the vibratory body or during the process, then the frequency which is measured is called as the force frequency or induced frequency. Okay. Now I am running a shaft or rotating a shaft at the high speed. I am increasing the speed regularly as the induced frequency which is generated due to the external force continuously applied, right? The value of induced frequency is equal to the value of natural frequency which is generated during the free vibration are equal. Means the value of induced frequency is equal to the value of natural frequency. The condition which is generated during this is called as the resonance. Okay, and during this resonance, the speed which is measured by the shaft is called as the critical speed. Okay, so the critical speed is the speed of the shaft or speed of the shaft when the resonance is produced, when the resonance is induced, the speed is called the critical speed. Okay, or you can write the definition as the speed at speed of shaft when the resonance is produced. The speed of shaft is called as the critical speed. Right? So that's it for today. We have studied, we have seen for the over damping conditions, under damping conditions, and the critical conditions. Next lecture. Thank you.